All right, hello everybody. Uh, this is chapter one, part one of Do Strategy. So let's get right into it. So let's pull out the notepad. All right, Brad Sanford, that is me. I'm the founder of Do Strategy, and I'm a Do strategist. Yeah. So what is Do Strategy, right? That's probably why you clicked on the video. You're wondering, trying to get more explanations and stuff. So Do Strategy can be defined as mathematical postulate that states the more consecutive successes you observe in a row, the higher the probability of a failure becomes, based on parameters, of course. And those parameters, well, let's start with P, which equals the base probability of something occurring or of a success occurring. Pretty self-explanatory there. And in this, so this Desmos graph, so we're gonna, for today's video, we're gonna have it based for, or it's gonna be set up for a coin flip. Just to make it nice and simple for everyone. Um, Keep it nice and introductory, if you know what I mean. So P is 0.5. Probability of a, let's say, a success in this example, let's say, is going to be a head. So probability of a head is 0.5. All right, it's pretty common knowledge. Everyone knows that. So this is the equation. So it's y equals 1 minus p e to the t minus x minus a all over t minus 1 to the all over d. And that's going to be restricted with the domain of x is equal to or greater than or equal to a. And then we have this equation I will explain later. So now that we got that out of the way, so yeah, P, probability of a success happening. T is equal to 2 over P, which intuitively it's just T stands for timeline, so how many observations it should take to observe a success. That's not in like probability, that's in like, so a coin flip, it should take you 2 observations, 2 coin flips to get ahead, statistically speaking, right? 50% chance. And then it's multiplied by 2. Why? Because that's what I found in my findings. A equals t minus 2, which is how many observations it should take to observe a success, just divided by 2. So, well, it's not, it's just the t divided by 2, but it's A is just the timeline, yeah. D, do multiplier, get into that later. So D stays at 1 here, so the timeline, so t equals 4 because 2 divided by p, so 2 divided by, so 2 divided by 0.5 equals 4, right? So that gives us our t. That's why t equals 4 here. And a is just 2 because a equals t divided by 2. 4 divided by 2 equals a. 2. Bang. So this, so what are you looking at, right? What is this graph? So first things first, this graph will never touch 1 because if you zoom in close enough, see how it doesn't touch 1? See? That is because I can never guarantee you, I can never guarantee 100% that it's anything is going to happen unless the base probability is 1. Other than that, I can't guarantee that because just not something I do. So after one coin flip, still 50% chance, right? There's no do strategy applied to it. We don't know. It's just one coin flip. Like, let's say the first person to ever pick up a coin, flipped a coin, there was no do-ness to it, right? It's the first coin flip ever. It's a 50% chance. It's either going to be heads or tails. We don't know. So second coin flip, same thing because it's still another 50% chance. Even though we got one tails, there's still a 50% chance that it can be tails again. So there's why it's after 2 coin flips, still 50% chance. This is where the do-ness comes in. So now let's say you've gotten 2 tails in a row. Like that's kind of weird. Third coin flip, 61% chance, 61.1% chance that it's going to be a success or head in this case scenario. Okay, let's say third coin flip rolls around, it's still tails. Weird, right? You go to 4, bang. odds increased. Now you have a 69.7% chance of it being ahead. All the way until, I mean, you start getting up here. Let's say we got 15 tails in a row. I mean, you're looking at 98.1% chance of it being ahead. But again, can't guarantee that. Can't guarantee the one. I can't guarantee it's going to be a 98% chance, but I can never guarantee that it's going to be ahead after the 15th or whatnot flip. So that's that. And then this equation right here is just this horizontal line showing that anything before the second flip, it's just a 50% chance we don't know. There's no do-ness attached to that. So let's say the probability of, I don't know, me like eating pizza is once every 7 days, so once a week. So timeline times 2, so that goes to that goes to 14. This goes to 14. This goes to 7. So now what's happening here is like day 1, it's just 50% chance because like I said, it's a 1 out of 7 chance that I eat a pizza. So bang, first day 50% chance, second or whatever, all the way up until 7 days. So now if I haven't eaten a pizza, so it's been a failure every day, I haven't eaten a pizza in a week, 7 days. Now the 8th day, now there's some do-ness attached to it, right? There's some do-ness attached because I usually eat a pizza every week, but now I haven't. Now it's the 8th day and I haven't eaten a pizza. So now that's when it starts going up. So this line is just showing, look, there's no do-ness from day 1 to 7. There's no do-ness because that's just the base probability of me eating a pizza. So cool. Now, do multiplier, right? So do multiplier is the do probability divided by the base probability. So let's go back to our coin flip example. So the do probability divided by base probability. So the do probability is just the y. So let's say after 5 tails in a row, I have a 76 or 0.764 for my y. So that's the do probability divided by the base probability, and the base probability is just p, so 0.5. So 0.764 divided by 0.5. So my do multiplier is 1.528. So what does that mean? That means if you take the base probability, 50% chance, multiply it by 1.528, you get the do probability. So how does that help in a situation, right? Why won't you just look at the graph and get it? So let's say I flipped a coin 10 times yesterday and it was all tails, and I got distracted. I was like, whatever. Or no, I flipped a coin. I don't remember how many times it was, but I flipped it a lot and it was all tails. So I'm like, dude, a head is really due. So I don't know the exact numbers here because I don't remember how many times I flipped it. So, but I can remember, oh, the do probability or the do multiplier was about 1.3. Okay, so take that graph. So do multiplier is about 1.3. So you put the do multiplier up to like 1.3. See how that shifts the graph up? See this? It shifts it up. So do multiplier is 1.3. So now the second flip, it should be a 50% chance, but since I'm carrying over my do-ness from yesterday, you can carry over do-ness. Once you carry it over, now you got a 61.5% chance on the first flip, on the second flip. Even though it should be a 50% chance, it's a 61% chance because you're carrying that do-ness over. So that's just a little side note for the do multiplier and how you can apply that to your daily life. And then so now that we got the equation out of the way, we're going to explain the Volpe error. So this Volpe error, I'll introduce them later, but the Volpe error is basically, so someone could come up to me, right? Brad, when is, well, they would come up to me because I'm the only do strategist as of right now. So they'd be like, do strategist, when is the sun gonna stop burning and turn into a supernova or whatever it turns into after it dies? I would say I don't know. That is the Volpe error because I can't apply any do-ness to something that hasn't happened, right? It's like I said, the first caveman to pick up a coin and flip it. I couldn't tell him. I couldn't tell him if it's gonna be heads or tails because I don't know. It's there's no do-ness attached. It's the first time it happens. I'm sorry, I can't help you on that one, right? Something we'll cover later, not today. There's do strategies within do strategy. So the more do strategy fails, the higher it is to uh, succeed. Pretty easy stuff there. Um, so this all kind of ties back to the central limit theorem, which is as the n number of observations goes toward infinity, the sample mean converges to the population mean. So with coin flips, I have my trusty website here. So we go, so simulate probability of a head with a fair coin, right? So 1,000 flips. So head, there's been a little more heads than tails. So overall, this next 1,000 flips, there's going to be a little bit of do-ness attached to tails. Because if I flipped a coin a million times, this proportion is going to be pretty much 0.5. It's going to be 0.5, right? So there's going to be a little do-ness, not a lot. Probably. So this is where the do multiplier comes back in. So you'd go do multiplier probably 1.03 to the tails, probably 1.03 tails. So now the first flip, or the second flip, now you got like a 51% chance of it being tails. It's not quite a 50-50 anymore because of the central limit theorem. So let's see. Well, it's a little more heads, just barely a little more heads, because the do-ness is attached to the tails. So now, there's still the do-ness attached to the tails. So let's do 1,000 more flips. I didn't really see what happened there. So this proportion should go to 0.50. So let's just start ripping 1,000 coin flips. See how it's getting. Yeah. See how it's getting closer. See this? See, it's getting closer to 0.50 every time. See, look at that. So I've done 22,000 coin flips, and the proportion is pretty much 0.5008, and there's only been 18 more heads than tails, because and watch. So I'll go up to like 30,000, and I guarantee it's gonna be proportion gonna be even closer to 0.5. See that? Yep. See? Now there's only been. See how tails overtook it. There's more tails in those next 8,000 flips because tails had that do-ness attached to it. So let's go up to 35,000, and I guarantee it's going to be heads, a lot more heads. See this? See? Now there's more. See, there was like 15, I think it was 15 more heads in that 5,000 because there was that little do-ness attached to the heads. So and I didn't make this website. This is an unbiased website with real statistical analysis and all that good stuff. So I don't know. Don't hate the play, hate the game. You know what I'm saying? So you can apply do strategy to anything. Yeah, you read it, you see it, it's possible. So that will be covered in the next videos and chapters and lectures. Shout out Michael Volpier. It's named after him. He was the backbone of the equation. I say backbone, he helped create it. I made some finishing tweaks on it, but he helped get me the idea because he's a pretty smart guy. He is Bachelor of Science of Economics at Duke University. Matthew Knox. Matthew Knox helped me with the A, shifting it over. He gave me the shift. I put the shift in the equation, and that is called the Matthew Knox clarification factor, MK for short. And he is currently pursuing his Bachelor of Science in Computer Science, Bachelor of Science of Electrical Computer Engineering with a concentration in machine learning at Duke University. And Cole Resnick, shout out, early philosopher and advocate for do strategy, and potentially making his way to become the next do strategist. He is currently pursuing his Bachelor Science of Economics at Duke University. And that is all I have for today. Thanks for watching, and I will make another video once I discover more findings.